Welcome to Lecture 10, Clustering Graphs and Network Data. In this lecture, we are going to first introduce basic concepts of graphs and network clustering. We'll introduce graphs and networks and their representations. We'll introduce typical evaluation measures, discuss the approaches for graph clustering. Then we'll focus on spectral clustering and scan an algorithm for density-based clustering of networks. First, we are going to discuss graph and network clustering, some basic concepts. First, we know most real-world data are interconnected, forming gigantic networks or graphs. Among all kinds of networks, we can categorize them into homogeneous networks versus heterogeneous networks. Homogeneous networks are those whose vertices and edges of only one type. For example, for web search engines, we look at click-through graphs or web page graphs. They are of one type. For social networks, friendship networks, co-author networks, they are also one type vertices and edges. For heterogeneous networks, vertices and edges are of multiple types. For example, we just look at two-typed graph. For example, customers and products, they could be linked together. Authors and conference, they could be linked together. Of course, authors and authors also can be linked together, but essentially you can see is two-typed graphs means you only have two kinds of vertices. Okay. For multiple-typed graphs, that simply says within a network, you may have multiple typed nodes and edges. Just give you a simple example like research networks. A research network like DBLP, you may have authors, papers, venues, and keywords. They may interconnect each other, like authors may write papers published in certain venues and using certain keywords. Okay. Similar things as medical networks, you may have doctors, patients, treatments, drugs, all these things. Freebase can contain much more different types of entities, and they interact and link to each other. So we want to distinguish some concepts like clustering, graph partitioning, and community discovery. Clustering, usually you try to group objects into groups. It can be hard, like k-means, or soft, like EM. And it can be complete or partial. It can be balanced or skewed. However, for graph partitioning, most people mean is hard partitioning, hard grouping. And it's complete. It means all the nodes and edges in the graph is somehow partitioned into different parts, different partition. And typically they are balanced. You try to balance them instead of get a singleton graph. For community discovery, usually it can be partial, means even some nodes you are not including certain community, it's quite okay. Because we are often interested in only finding the density connected components. We're not interested in the cluster assignment of every vertex. Let's look at the major challenges for graph clustering. That means how to find good cuts. They are very challenging because the first thing is high computational cost. Many graph cutting algorithms or problems are computationally expensive. You need to trade between efficiency, scalability, and the quality of clustering. And also, the graphs can be quite sophisticated. It may involve weights, involve cycles, or self-cycles. It could be very high dimensional, since one graph can have many vertices. Okay? If you think every vertex is a dimension, the dimensionality of the matrix actually is the number of vertices in the graph. So this could be really big. Another issue is sparsity. Since a large graph is often very sparse, that means each vertex on average only connects to a very small number of other vertices. If you think about a complete connected, means everybody connects to everybody else. In a large network, usually it's not the case. To that extent, a similarity matrix from the very large sparse graph, it can be very sparse matrix. So we have to find efficient method to solve all these problems or challenging issues.